Welcome back. In this video, we're going to go over section 3.4, which is about graphing linear inequalities in two variables. So the plan overall is to look at what does such an inequality look like, what are the solutions to an inequality of that type, and then how do you graph those solutions. So let's start by taking a look at what a linear inequality looks like. So variety of forms, ax plus by is less than c, greater than c, less than or equal to c, or greater than or equal to c. So in short, you could think of it as kind of like a linear equation, ax plus by equals c, but instead of an equal sign, you have one of the four different inequality signs, less than, greater than, less than or equal to, or greater than or equal to. That's what an inequality looks like. And here you'll notice the little star I put on looks like. That means that any kind of algebraic equivalent could be also considered a linear inequality in two variables. For example, all right, so as I was saying, any algebraic equivalent would also be considered a linear inequality in two variables. So while x plus y is less than 10 is a linear inequality in two variables, if we were to subtract the y from both sides and make it x is less than 10 minus y, that's also an inequality in two variables. So take a look at some other examples. 3x plus 4y is less than 2. Y is greater than or equal to 7x minus 1, 8. In this case, the y was isolated. X minus y is greater than 10. 2x minus 3 is greater than 6y. All examples of linear inequalities in two variables. The next thing to look at are what the solutions to such an inequality are. And the solutions are going to be ordered pairs x, y. And so, for example, we have the inequality y is greater than x plus 4, and we want to decide which of these pairs is a solution. So let's substitute 0 in for x and 0 in for y first, and see. 0, that's y, is greater than 0, that's x, plus 4. Is 0 greater than 4? The answer is no, and so this one is not going to be a solution to that inequality. Let's try the next one. Y is greater than x plus 4. Here our y is 6. 6 is greater than 2 plus 4. 6 is not actually greater than 6, and so that's not a solution. Hopefully this will be. Y is greater than x plus 4. And so here 12 greater than negative 8 plus 4. 12 is greater than negative 4. Yes, that's true. So that is a solution. Okay, so primarily when we're giving solutions to these linear inequalities in two variables, it's going to be graphically. And so to do that, I wanted to review how a linear inequality in one variable is going to look. So let's say that we have the inequality 2x plus 1 is greater than 11. We'd solve this and also graph the solution on a number line. So how you solve this, the algebraic steps, you'd start by subtracting 1 from both sides. So 2x is greater than 10, making it so that x is greater than 5. And then for a picture, the boundary between solutions and non-solutions would be at 5, right? It says x is greater than 5, so the solutions are on the right side of 5. And that's a picture of all the solutions to x is greater than 5. And those are the solutions to 2x plus 1 is greater than 11. So here, the boundary between solutions and non-solutions was a point where x is equal to 5. So we could look at this solving inequality process as finding where the boundary is and then deciding which side the solutions would be on. In other words, let's say that we consider the corresponding equation, 2x plus 1 equals 11, and then solve that, 2x is equal to 10, so that x is equal to 5. So again, we're going to look and we'll find that, well, 5 is going to be the boundary between solutions and non-solutions. Let's test a number on one side of the boundary or the other and see where if that's the solutions or not, because we know they'll be on one side of the boundary or the other. So I'm going to try 6. We're going to test 6 in our inequality. 2 times 6 plus 1, is that greater than 11? And the answer is going to be yes. Since that solution to the inequality is on the right side, that means all the solutions are on the right side. That method of finding the solutions to this linear inequality by solving the equation and then testing a point on one side or the other is basically how we're going to do this for the two variable case. So definition, for one of these linear inequalities, we have a boundary line. That's going to be the corresponding linear equations graph. So ax plus by equals c is going to be the boundary line for all four of these different inequalities. All right, so the next example we're going to do is graph the solutions of the inequality x is greater than or equal to 3. And the method that we're going to use is by first graphing the corresponding equation, which is x equals 3. So I've just changed the inequality sign into an equal sign. We're going to graph that line. That line is a vertical line, and it passes through the point 3, 0. So let's go ahead. Sorry about that, Zoom crashed again. All right, so that is the boundary line that we've graphed. And so next we have to decide which side of the boundary line these solutions are going to be on. So you want to test one point on one side of the line or the other. It doesn't matter which side that you contains the point that you test. I'm going to use the point 1, 3, just because that was a point that I happened to pick. So let me actually use one that doesn't involve a 3. That's probably better. I don't want any coincidences. Let's use 2, 1. All right, so we're going to use the point 2, 1 here, and we want to test that in the inequality x is greater than or equal to 3. So at that point, x is equal to 2, and so we can substitute that into the inequality. 2 is greater than or equal to 3. No, it isn't. So this point is not a solution to our inequality. That means that none of the points on the left side of the line are solutions. So all of the points on the right side of the line make up solutions. The solutions are all on one side or the other, just as when we had our linear equation in one variable, or inequality in one variable, all the solutions were on one side or the other of the boundary point. Here, all of the points that make up solutions are going to be on one side or the other for the boundary line. All right, let's try one more. Here we're going to graph the solutions of y is less than or equal to -2. So the corresponding equation is y equals -2. And that is a horizontal line that passes through the point 0, -2. So let's go ahead and draw that. So now, again, we have to decide whether the solutions lie above or below this line. So we want to test a point that is not on the line. It doesn't matter which point we pick. I'm going to choose the point like -4, 1. Let's say I just happen to choose that. So let me put the coordinates of this point into our inequality. Here the y is 1. 1 is less than or equal to -2. Here the answer is no. That means the solutions are on the other side of the line. And so we're going to put some shading on the graph to show that that below the line contains all the solutions to our inequality. Okay, so in general, the steps to follow, and then more examples. So the first thing to do is to graph the boundary line. So change the inequality sign into an equal sign. This gives you the equation of a line. Graph that. And when you're graphing that, if the original inequality sign was less than or equal or greater than or equal, you'll use a solid line. If the line or if the inequality sign was strictly less than or strictly greater than, you'll use a dashed line. And that is how we show either inclusion or non-inclusion. So once again, going back to the single variable case, if we had x greater than 2, how you show that on the number line is the fact that the 2 itself is not included is using an open circle. or maybe a round parenthesis, either way. And then if you wanted to show inclusion, x is greater than or equal to 2, that is, the 2 is included, you might use a solid dot or a square bracket. So either way, we have some way of showing whether or not the 2 itself is included or not. How you show this doing the two variable case is if the boundary is included, that is, you've got the or equal to, you draw a solid line. If the inequality does not have the or equal to, the boundary is not included, and you use a dashed line. Once you've got that done, you test a point that is not on the line. Once you've tested that point, you say, okay, well, is it a solution or not? All the solutions are on one side of the line or the other. And so you shade the side containing the solutions. Okay, so we're going to try that next. We want to graph the solutions of y is less than a half of x minus 4. So our corresponding equation would be y equals 1/2 x minus 4. So we want to graph that. So let's make a xy axis. The y-intercept here is -4. And then we'll have a slope of 1/2. So y-intercept of -4, and then the slope is 1/2. So I'll go up 1 and right 2 to get another point on the line. On this one, notice that it was strictly less than. So when I go to draw the line next, I'll be drawing it using a dashed line. And that represents the fact that the line itself does not make up part of the solution set. Okay, once we've done that, we check a point not on a line. Often it's convenient to use the origin for this. 0, 0. Zeros are easy to plug into things, so let's do that. 0 is less than a half of 0 minus 4. Make sure that you're plugging your test point into the inequality, not the equation. So 0 is less than -4. For this one, the answer is no. So that means the origin's not a solution. So that means that none of the points that are above the line are solutions. So all these solutions are below the line. All right, here's one more for us to try. In fact, why don't you try this one? Pause the video and try this one yourself, and then restart the video and see how you did. All right, so our first task for this is to graph the corresponding equation. So that will be x minus 4y equals 8. And so to do this, I'm going to use the intercepts. Okay, because it's in general form, that seems like the easiest way to do it to me. So when x is 0, y will be -2. When y is 0, x will be 8. Okay, so let me put those points on the graph. So we have 0, -2, and then 8, 0. I like to label the intercepts just to help people read it better. On this one, it was less than or equal to, so we're going to be graphing the line with a solid line instead of a dashed line. Okay, and so now want to test a point not on the line. So once again, I'm going to use the origin just because 0 is easy to calculate with. So we're going to test the origin. Okay, so 0 minus 4 times 0 is less than or equal to 8. 0 minus 0 is less than or equal to 8. It's true that 0 is less than or equal to 8. So that means that all of the points above the line make up solutions. So we'll go ahead and shade everything that is above that line. So the solutions to our inequality are the points on and above that line. Okay, next we're going to try 2x plus 3y is less than 6. So for this one, corresponding equation first. 2x plus 3y equals 6. And once again with the intercepts. When x is 0, y will be 2. When y is 0, x will be 3. On this one, it's strictly less, so we will be graphing the line with a dashed line. So let me get those intercepts on, 0, 2, and then 3, 0. And then let's draw a dashed line. Okay, and then once again, we need to decide where the solutions are. So I like to test the origin, so we'll stick with that. You don't have to, but you do need to test a point that is not on the line. 2 times 0 plus 3 times 0 is less than 6. So 0 plus 0 is less than 6. 0 is less than 6. It's true that 0 is less than 6, and so that means that the origin is a solution, and so all the points below the line are solutions. Okay. One thing to note is that when we were doing inequalities in one variable, when we came down to, like, let's say x is less than 2, we would write our answer in interval notation. There isn't a kind of interval notation for this linear inequalities type problems. The graph is it. That's all we're really expecting for this. So you don't have to learn some kind of two-dimensional interval notation for this. Okay, here's one more, and then we will do a story problem. All right, so here x plus 5y is greater than or equal to -5. So once again, with the corresponding equation for the boundary line, x plus 5y equals -5. Okay, intercepts. When x is 0, y will be -1. When y is 0, x will be -5. So we'll plot the point -5, 0, and the point 0, -1. Our original inequality had a greater than or equal to in it. And so it's got the or equal to, so we're going to be using a solid line on that. Okay, once again, we need to test a point not on the line. And so I've been using the origin a lot, so let me use something different this time. I'm going to test -3, 1. Okay. So x is -3 plus 5 times 1. We want to know if that's greater than or equal to -5. So as you can see, it's would have been easier if I'd picked the origin, but that's okay. -3 plus 5 greater than or equal to -5 is 2 greater than or equal to -5. Answer is yes. So the point above the line, our test point was a solution, so that means that all the points above the line make up solutions. And so we'll go ahead and shade those points. Okay, so that will do it. All right, to finish up, we're going to take a look at an example. So the story here is that Pat works 2 part-time jobs. One is at a grocery store that pays $10 an hour, and the other is babysitting and pays $13 an hour. Pat wants to earn at least $260 a week. We want to know how many hours Pat needs to work in order to make at least $260 a week. So the steps to follow, we're going to let X be the number of hours worked at the grocery, Y the number of hours babysitting, and then we're going to write an inequality representing the situation, and then we'll graph it, and then we'll worry about part C when we get there. Okay, so let's start by getting that inequality made. All right, so it says we're going to let hours be the grocery store, X as the hours worked in the grocery store, and Y will be the hours babysitting. So Pat makes $10 an hour at the grocery store. So $10 an hour times X hours at the grocery store, and then $13 an hour for babysitting times the number of hours spent babysitting. And Pat wants to make at least 260 a week. So more would be okay, definitely good. But it doesn't have to be exactly more than Pat wants to make at least. So it could be equal to 260. So we'll have 10x plus 13y is greater than or equal to 260. All right, so let's work on making the graph for that. 10x plus 13y equals 260. I'm going to graph the boundary line first. So once again, with the intercepts, I think that's nice. If x is 0, y will need to be 20. And then if y is 0, x will need to be 26. If y is 0, x is 26. Okay. All right. So for this, on the grid here, I'm going to make each mark worth 2. So give me a minute to draw the scale. All right. So vertically, we need to get to 20. We're going by 4s. All right, there we go. All right, so on the vertical axis, that was y, that was the hours babysitting. And on the x-axis was the hours at the grocery store. All right, so then let's make our picture. So when x is 0, y will be 20. When y is 0, x will be 26. Since our inequality was a strictly greater than, we're going to use a solid line to draw it. You'll notice in here that I've drawn the picture just in quadrant 1. It doesn't make any sense for us to have negative hours babysitting or working at the grocery. All right, so just positive numbers for both x and y. All right, so then the next thing to do is be to test a number in the inequality. And so the origin here is a good choice. And that makes some intuitive sense that if Pat doesn't work any hours, then what are the chances that Pat makes $260 working no hours? Pretty sure that's not going to happen, right? And so it has to be the other side. And that's consistent with our expectations too, that the upside for the, on the other side, above the line is going to make up the solutions. If Pat were able to work like tons and tons of hours, then definitely we'd reach that target of $260. All right, so now it says find 3 ordered pairs that would be solutions for the inequality. Explain what each means for Pat. So let me take off some of the shading so that I can draw on top of it. So a couple of solutions. It looks like if Pat worked 20 hours at the grocery and 8 babysitting, then that would do it. I'll leave it to you to figure out how much money Pat's going to make in that case. Or 12 hours at the grocery and 20 hours babysitting would also do it. Or even 28 hours at the grocery and no hours babysitting, that would also do it. Okay, so that takes us to the end of this section on linear inequalities variables. Let me know if you have any questions and have a great day.